I would like to speak about the heterogenic and homogenic heating in oncology, like two different paradigms. My outline is simple. I will start with homogenic challenges, so the challenges of the homogenic heating. Local regional hyperthermia method has a lot of electromagnetic techniques. The most important, the most well-known parts are isothermic, characterized by isothermic heating, and it has three different kinds: radiative, like antennas, capacitive, and magnetic heating. The aim is that we are heating up the tumor mass as homogenic as possible from outside, and then measuring the temperature like the effect of the result. The isotopes heating is a different approach. It's non-temperature characterized, but only dose characterized. Heterogenic heating could be like artificial local absorbers, nanoparticles, seeds, rods, and interstitial. When we have a lot of absorbers inside the cell, inside the tumor, we put it in artificially, and then these absorbers are absorbing the energy, and this energy which is absorbed by the internal absorbers heat up the tumor mass itself. It's heterogenic, and we can learn from this one that how to find naturally selected absorbers inside the body and not necessarily artificially put something in. Good example, the radiotherapy, when we have an isodose around the things and really focused on the tumor, but the isodose attacks the very nanoscopic parts, the double strengths of the DNA. So this one is the main point to cause apoptosis. We learn this method on such way that we choose impedance matching the transmembrane proteins and exciting the cluster of transmembrane proteins we call membrane rafts for apoptosis also on the same way. It's a death receptor which we would like to excite. Of course, the key points are the focusing, which takes care about the physiological, therapeutical, and safety issues. The challenge of heterogeneity is present in homogenic heating. Why it is so? For example, here is the body. This is a target which you would like to heat up and the bolus around. And we can see that after 7 minutes, the target grows up to more than 2 centigrade, but the bolus is more heated. And we have a very high heating in a hotspot somewhere else. And after an hour, we have different part of hotspot, and the 9% of target is very high, but the bolus is even higher. So it means that we cannot be sure that absolutely homogeneously focusing the things, and even if it is focused, then in the focus we have in 10% of the tumor mass temperature, and 30% in the tumor mass less temperature, 50% in the tumor mass even less, and the mean will be around the tumor. And this heterogeneity shows the temperature changes from the center to the border, maybe that a few centigrade. The other one is the blood flow heterogeneity, because the blood flow is on the body temperature, so it's a cooled media. So if we have a temperature sensor near to the arteries, then it measures less temperature than far from the arteries. The other problem is the measurement itself, which has heterogeneity. Why it is so? Because if we have different tumors, then the different tumors are heated regionally, but the invasive temperature measurement cannot be done in all of the points of the region, so we are using the non-invasive temperature sensors in the lumen or cavities or something, and then these are far away from the real tumor, and depends on the hotspot, depends on the different other things, so we cannot be sure that what temperature we are really measuring. The bioelectric heterogeneity is even more affecting. We have a current density through the body, and the excitation depends linearly from the current density, while the heat effect, so the Joule heat, depends on the square of the current density. The different absorbers, heterogenic absorbers, could done conductively polarization like electron excitations and so on, aggregations. So it means that these are really natural heterogeneities which are existing inside, even if we would like to do a homogenic heating. And which is important that this heterogeneity is very differently recognized by different currents. If the current is zero, so it's a zero frequency, so it's a direct current, or a lower frequency or higher, this we call dispersion relations, and we can have alpha, beta, delta, and gamma dispersion depending on the different ranges of the frequencies which are applying. Of course, these frequency ranges are overlapping, and these overlapping makes the very complex points, because the most complex interactions are, of course, in these overlapping regions. We had chosen the overlap between the beta and delta dispersion, which gives a very special facility for exciting the membrane rafts. If we see that what are the effects of different dispersion relations, the electromagnetic effects are ionic effects in alpha, capacitive charging in beta, dipolar mechanism in delta, and scattering region in gamma. In the water state, we have dielectric loss in alpha, dielectric loss in the crystalline spaces, not ice, but it's lichen ice, in beta, so molecular water in alpha, and crystalline water in beta, and then in bound water in delta, and dielectric loss in the free water in gamma. Which is more important, what are the bioelectromagnetic effects, which is the membrane effect, intercellular charging, then charging membranes, orients proteins, dipolar mechanisms, and free water resonances. So we can see that these two are very important for us. It's a rotational relaxation of the membrane proteins. So it means that we are concentrating on this one. Concentrating because this is a protein bonded water is exactly targeted by this frequency. But of course, we would like to use the other membrane effect, the dielectric loss in the water, and all the other membrane points. So we use the alpha dispersion as well, but this used on such way that this high frequency carries the modulation, and the carrier allows that the modulation acts in the alpha dispersion also. So we are acting in both the regions. The other point of the heterogeneity is the frequency dependence of the penetration. So the penetration depth goes down, decreases by the frequency. So at 13.6 megahertz we have about 18 centimeter penetration. But if we have current well done through the body, then the current starts from one electrode, ends to the other one, so it means that it has no such classical meaning of the penetration depth. So these heterogeneities allows the selection of electromagnetic wave which we would like to use. The heterogenic selection, then the consequence, we can see the heating consequence and the excitation consequence with different proportion of the J function. The excitation from the initial to the end goes through a transition state which is excited. The other one in the macro heterogeneity, in the micro heterogeneity, when the current goes through the tissue, then the current much easier goes between the cells, so in extracellular liquid, than through the cells, because through the cells they are barriers of the membranes, and this limits very much the real current density. So if we see that what is the heat effect, so this SI effect, heat effect in the different cells, then we can see that the extracellular, the intercellular absorption, the extracellular absorption, and membrane absorptions are different, and the ratio between these are very definite here. So we are using this area for membrane absorption also, so it's one selection factor. The other selection factor is electric, because the cell has different electric properties inside and outside, and we can calculate that the 60 Hz application makes the maximum 8 millivolt per nanometer maximum excitation, while 10 MHz has 12 millivolt per nanometer, and 1 GHz has 7 millivolt per nanometer. The maximum is around 10 MHz. The other point which we have to take care, that if the energy absorption is too high, then we lose the selectivity. So it means that we have to have a consideration that J square must be not overtake the J linear, because the J linear makes the real excitation, so the selection. The change of the nanoheterogeneity is again a challenge. You see that here is the cell and different parameters inside and outside and the membrane of the cell, and differences in the current, like I had shown before. And with this calculation, the heating of membrane rafts is very clearly shown that the current density, which is linear with J, is much higher in rafts than in other areas. In ampere per square meter can be measured, and in watt per cubometer you can measure the absorbed energy. So it means the temperature. This is the excitation. This is the temperature, thermal effect, non-thermal effect. It means that the thermal effect is also concentrating on the raft, that like the non-thermal effect concentrates on the raft. The next is a pattern selection by radiofrequency current, which means that the structural characteristic can be measured by an American lab, measured it, that resistive and capacitive parts are very significantly differ from each other by their radiofrequency effect in resistive and capacitive part. So, we are ready for molecular changes which we can measure in the tissue selectively, molecularly. This is the current which goes around the cell, and only a small part inside, and then this excitation and heating, it makes the thermal heat production in these membrane points, the rafts, and these rafts are clusters of molecules which are excited by non-thermal effects. So it means that this is the synergy, or at least an addition, of the heating, thermal effect, and non-thermal effect together. And this non-thermal effect, which is in the selection had been chosen, excites the DES receptor and fast-fed complex with it, and then you can measure that the trial DES receptor and fast-fed, the part of the complex things, 8 hours after the treatment has much higher value than it was before. We can show some experiments. We had a lot of experiments before, but some experiments we can show. So this one is the time after the treatment, 5 hours, 10 hours, and this is the anti-apoptotic and pro-apoptotic processes. and then you can see that the proteins which makes anti-apoptotic effects after the treatment within 5 hours are lowered from the standard level, while the pro-apoptotic proteins are growing from the standard level. So it means that we are helping molecularly with these molecules the apoptotic process. Also, we can see the other molecular effects with the caspases. The major extrinsic pathway uses the caspase 8, the major intrinsic pathway, the caspase 9, and the executor of both is caspase 3. And we can see that in all caspases, so in all apoptotic processes, the modulated hyperthermia on the same temperature, much higher than capacitive, other capacitive, so homogenically capacitive treatment in 42 or water bath in 42. It can be shown in various pathways by excitation of modulated hyperthermia. The trial complex, the DES receptor complex, is excited, and then comes the extrinsic pathway with caspase 8, caspase 3, and apoptosis. So this is the main path of the apoptosis. And this can make an excitation of mitochondria by BID and then BID, and then intrinsic path started through the cytochrome C and cytochrome C complex with caspase 9, and then makes the apoptosis again with the same executor. But the mitochondria itself has also stresses, not only the from caspase 8 coming the signal, the thermal stress and electric excitation, and this makes the apoptosis-inducing factor a caspase-independent way, making apoptosis. The other interesting point to producing the ROS molecules and reactive oxygen species, you see that these are exciting the DNA and helping DNA fragmentation, and modulated electrohyperthermia also makes an internal fragmentation processes to DNA. DNA produces P53, and P53 induces Bax, and Bax promotes the mitochondria apoptosis. And of course, it's very nice that so many apoptotic pathways are available, at least 4 different. But you see that the homeostasis is not such that can go everything in one direction. But we have more helper, the E2F1, which backs and other. But the blocking is a BCL2. So it means the BCL2 tries to block the mitochondria processes, but P53 controls it with in interaction with PUMA, blocks the BCL2. So it means the blocking of blocker makes available that mitochondria act in the apoptosis. Furthermore, we have a XIAP which would like to block the caspase 3, the absolutely central executor of these internal and extrinsic and intrinsic pathways. But modulated electrohyperthermia excites the blockers of the XIAP, septin-4, SMAC-diabolo, and HTRA, OMI. So it means that we are blocking all the blockers which are in this way important. On the other hand, other kind of blockers are available. These are the heat shock proteins, inside heat shock proteins. So that is why HSP70 and HSP90, they would like to block all these processes which are going in these pathways. But the HSP60 tries to help the caspase 9 to turn to caspase 3, so it means it's a little helper, but dominantly the protectors, so the against of the apoptotic process acting here. but the intercellular stress which we have altogether is so high that the HSPs are exhausted, and this exhaustion means that the apoptosis is going on. All molecular steps which are here are published by different labs and many different publications. Apoptotic conditions, so only one simple show that how it's going on. The in vivo mammary carcinoma isograph, which is a triple negative mammary carcinoma, you can see that the destruction ratio and apoptotic executor, the Cleve-Caspar-3, going absolutely together. So it means that the main destruction factor is the apoptosis. And also it shows the HSP development is overtaken by the tumor destruction. So again, shows that the apoptosis is going on. Another experiment shows the same, like the intercellular HSP70 is down, while the destruction factor is up. But which is very important, that we have another peak of the HSP70, which is extracellular, and this extracellular HSP70 makes possible to inform the immune system about the immunogenic problem of the cell, and the immune system can develop, the adaptive immune system can develop anti-cancer immune reactions. The thermal specialty also can be measured. So, for example, this one is the water bus measurements, so homogeneous heating, 42, 45, 49, 59, 48, 58 centigrade. And this is another capacitive, homogenic capacitive 42, and modulated electrohyperthermia in 42. You can see that really the homogenic heating has equal things, so the normal capacitive has an aim of homogeneity, which is fulfilled, but modulated electrohyperthermia had much higher effect than the homogeneous one. So if we have a calibration, this is the water bus reference calibration, and here is the modulated electrohyperthermia, then you can see that the modulated hyperthermia reaches the same apoptotic level, 5 centigrade lower temperature than the general homogenic heating. So it means that modulated electrohyperthermia rafts has 5 centigrade higher temperature than the homogenic area around. The same can be measured in vivo in murine model. You see that infrared hyperthermia in 42 has much less destruction level than modulated hyperthermia on the same temperature. Other experiment also shows the same. Here's the water bath reference homogeneous, and then here are the measurements of modulated electrohyperthermia in 40, 41, 42, and then you can see that always the rafts are at least 3 centigrade higher temperature, so making the same 3 centigrade earlier than water bath does. We can see that it's really the thermal factor is on, because the thermal effect, which is the Arrhenius plot, can be measured by modulated electrohyperthermia also, like in homogeneous heating. So it means the heating factor, the thermal factor, is active in vivo as well. The immune effects are very important one, and we are trying to do it as much as possible. What it means, we have the tumor microenvironment and exciting the raft in thermal and non-thermal way, like I had shown before, and this makes the apoptotic process on different ways of excitation. This one secretes the membrane HSP70, so it means the HSP70, the inside exhausted HSP70 goes outside of the membrane, which is an attractor for NK cells, or natural killer cells, part of the innate immune system. And then it means that this attack will be available to destroy the cell, because finds the cancer cells by this secretion of the HSP70. But when the apoptosis is going further, we call it the ICD, which is the immunogenic cell death, which immunogenic cell death produces extracellular HSP70, HMGB1 and calreticulin also in extracellular matrix. And these are making the antigen-presenting cells maturing the DC cells and producing T cells, which are owning all the genetic properties of the tumor cells. So it means they are producing tumor-specific immune reaction, which is the killer cells, helper cells, like members of adaptive immune system, and the gamma delta T cells, which are in between the adaptive and innate immune system, somehow a median between the two. And then these T cells are attacking the cancer cells everywhere in the body. So while the innate immune system attacks the cells which are chosen, these are, it means that making the MAH T70, the adaptive immune system and gamma delta T attacks the tumor cells everywhere in the body without external laboratory productions or laboratory activity. The complexity is the consequence of this all. So if we have a heating effect, which is energetically equal everywhere, and we have the exciting effect, which has a very special frequency peak somewhere, which linearly with the E, then of course this one pumps the ions through the membrane channels, which depends on the change of the potential, and the heating, so the other factor, is pumping the thermal machinery, which depends on the temperature differences. So it means it's a non-thermal and the thermal machinery of the membrane ionic spaces. This one is the non-thermal process of the excitation, like we had seen, and this makes a very strong force to make one direction effect of the enzymatic processes. So it means that we have then A0 initial state, and this is forced to go to the transition state and transition state to the end state, and this is the process of the non-thermal effect. The thermal effect also goes in the way, but this is a jump through the barrier, so the normal Arrhenius jump, and this barrier jump makes that one that the ion can go through the membrane, so pushes the ion through the membrane. It means that it makes the same line, very similar, but a different transition state and different end state at the end. When we have a normal enzymatic processes, then we have, let's say, without enzyme and with enzyme, different barriers, because the enzyme lowers the barrier of the thermal jumping. So it means it's a chemical lowering of the thermal effect. In synergy of the two effects which we have, the non-thermal and thermal, is such one that the non-thermal effect works like an enzyme, helps the transition state to lower this jump energy, and then the jumping is easier, so it can call this effect like an electric field enzymatic process, so works like an enzyme. And this is the main point of the synergy, and the final effect is really the effect of the synergy. So we have a complex result which is much higher, much more effective than any of the parts, non-thermal or thermal effects. At the end, we have summarized all the factors which I wanted to explain for you, and very, very important message that the homogeneity has a challenge which can be overtaken by heterogenic selection, and the molecular effects shows very well that the heterogenic selection can be done in molecular level, and this one can be used for immune effects, which immune effects enlarges the local treatment to global. It means that the local treatment became systemic. Everywhere will be attacked the far away distant metastases and even the circulating tumor cells, and then all the points are summarized in the complexity when the complex interaction between the thermal and non-thermal effects makes the result very effective and well stable without any hotspots and any uncontrolled points. Thank you very much for your kind attention.